A special thank you to the HVAC School for Techs by Techs. This is a live recording of the HVAC RFTM Symposium 2020 with Alex Meaney of Wrightsoft.
Will be a better balance system, right? It's going to be a better design system, and we do that automatically. That's actually the default setting of the software. You don't even know how to make that happen. It just does it. You have to know how to turn it off. And look at the loop that makes. Right? Compared to that first loop, it's no wonder I have to use bigger ducts. That's crazy bigger. Right? That's like 3 times the size.
You see the previous one again?
So, yeah.
I'm sorry.
That's all right. All right? Well, I didn't catch all of that, but no. So the same would apply to a flex system, guys. I'm not going to dwell. I know. Hey, actually,
That looks like a bow tie.
so it does. Fun fact.
That's Louisiana.
Fun fact. If you installed this perfectly, there's the rub. Right? But if you installed that perfectly, lower equivalent length than the sheet metal system.
Wow.
Resistance adds in series, not in parallel, and the shortest distance between 2 points is a straight line. No one who installs that is installing it perfectly, right? And very few people who install these design them properly. But if you were able to pull that flex duct correctly, see, it works great on paper. You get in the field, it doesn't end up looking like that, does it? Right?
I don't know.
So maybe it does.
I would argue
I'm not
that.
okay.
That's
I'm
Louisiana
agnostic
world,
for the time being until I get my brainwashing session from the sheet metal manufacturers at MyTech. I am for the time being agnostic when it comes to your duct product. Right? I think, and I'm a big believer of the 80-20 rule. I'm a big believer that 20% of the effort gets you 80% of the way there. So if I can't convert you from sheet metal or from flex to sheet metal, if I can convert you from doing a flex design that is using the ductulator to doing a flex design that you actually design and calculate a friction rate on, I think you're going to see 80% of the benefit there, right? Because that's a nice short loop, and nothing is ever this clean when they do this style of install, like 8s, 7s, right? This would be, by the way, the longer loop. There you go. By the way, speaking of an 8 versus a 7, and speaking of stuff we all already know, and we all already know this one, but all of us are guilty, probably. There's probably somebody out here who's the exception. But most likely all of us are guilty of forgetting this. It's not a 7 versus an 8. 7 versus 8 is not how this works. It's 38 versus 50. It's the transverse area of the duct. Okay? We think of duct as going up like this. 4, 5, 6, 7, 8, 9, 10, 12, 14, 16, 18, 20. Duct goes up like this. I can't read. 12, 19, 28, 38, 50, 63, 78, 113.
Oh, I want to get a picture of it.
I'll send you the whole thing. Anybody wants to email me. But
Now
some
you
people
tell me.
are better with the pictures.
That is cool.
Back to what I said, but I don't care, whatever. The best way to think of this, right, and to ask your technicians, you want to impress this upon guys who haven't had the kind of experience that people in this room do. How many 6s does it take to make a 12?
Oh, right.
4. It takes 4 6s to make a 12, not 2. Okay? Literally, think of a 12-inch circle. Now put 2 6 inches in there. How much extra room is there? Yeah. It takes 4 6s to make a 12, not 2. Right? And so we lose sight of the fact that the difference between a 6 and an 8 is a big freaking deal. Right? Even if you think of it in terms of percentages. Right? This is a 20% difference, not an 8% difference or 9% difference. I'm doing the math in my head and I'm screwing it up, but it's close. Right?
I like to think of line 6, because people
Line
say
6 same
7,
way.
8 inch and 8, no difference. I'm like, huge difference.
Some people actually, and if you would think this would be my way of thinking about it, pizza, right? Literally, an 8-inch pie versus the 12-inch pie. Look at the difference in cost there. It's because the 12-inch pie is way bigger, right? Because it's not linear. It's literally square inches. You know what that is? That's the square curve. That's what we got there. Actually, this is the square curve with a little hitch in it because it goes up in 2-inch increments after 10. Right? So, I sometimes forget I am the verbal equivalent of a steamroller. The more boring the information, the more animated I get. And that doesn't leave a lot of room for you guys. I told you to interrupt me, and everybody's just like, wow, yeah, cool. But I'm going to pause here for a second because I'm going to change gears a little bit. Anything that I just laid out there for you, did any of that just, seem wrong? Just like, I don't believe that. All right. And maybe we're just too shy to have the rest of the room come down on them, but...
All right, I'll do it.
Thank you. No, seriously.
Nothing about you.
Oh.
So no better.
But that guy over there...
Actually install 7-inch ducts.
That's a pretty good number.
Wow.
Yeah.
All day.
Yeah.
Everybody knows a 7-inch duct gives you 55 CFM, right?
Yeah. So that's good.
I've never installed
So
my
okay,
entire
all right. Do you use balancing dampers in all your takeoffs? You are forgiven. Right? So it'd be better to have a 7-inch, right? But an 8-inch with a balancing damper can pretty quickly become a 7-inch, right? It's the guys who don't use 7-inch, who aren't using balancing dampers, who are doing surgery with a sledgehammer out there, right? Because the increment between the 6 and the 8 is from 28 to 50. That's almost double, right? When you go from 6 to 8, you are just about doubling the amount of airflow you'll get out of that, all things being equal, and they never are. You don't use balancing dampers in that, that's surgery with a sledgehammer.
And I'd say, what I've learned through, the Facebook groups and getting to know, these guys from other parts of the country is it's very radically different around the country.
Oh, my God.
You
There's parts of the country you can't buy 7-inch stuff.
In my area, 977 is extremely common. And so
Yep.
it's home runs.
I never
Go to Arkansas, and it's a special order.
Yeah.
Yeah, well, that's what it is in North Carolina.
There you go.
We go up on a job with 9-inch duct. Go, what kind of jack leg? What is this?
Yeah.
And one of the things that I do with Wrightsoft is there's a way to teach it to stop giving you 7s and stop giving you 9s, so it will automatically give you 8s and 10s.
Yeah.
You can delete
I don't like using that. I like using it by either manually changing it or just leave. Here's a radical idea. If you're not using our materials list tool, so that Wrightsoft actually has to know what's going in it, if you're going to give it to your guys, tell them if it says 7, use an 8.
Yeah.
But now we know where the 7 should have been. And if you do air balancing, yeah! How about we just tweak those dampers on all the ones that were supposed to be 7s before we do our first pass with our flow hood? Think that'll maybe save us some time doing a balance?
What's nice?
So I like to have it give me the 7s and the 9s, even if I don't use them, because there's something that can save me time in the field. Save you time in the field. I'm going to the field. It's hot up there. Look at me.
In that same statement, I'd say it's nice because, in the program, that's where maybe I'm wrong, but I'll always go a step bigger if I have to get my bill of materials proper for what I can get from the supply house.
And that's another reason why that's my default setting is only go in.
Yeah,
into.
you can do that.
The other thing, being a contractor, is your guys are going to forget stuff on the truck.
Sure.
So there are less things to.
All right,
They're
well,
more likely to have extra stuff if they have.
So
less stuff
and you
to bring
can,
in.
and now this becomes a logistical back-end problem, but I can apply that library where it only gives you those even sizes after you print one out. So you can have one for your install crew or one for your balancing crew. Don't even give it to the install if you have a different balance than install crew. Some people do, some people don't. But have one where you've done that, and then just turn the setting on, and that's the one I'm going to print out. That's the one I'll order from. That's the one I'll give to my install team. Okay, and I realize I've committed this in there. I've talked about software that I haven't shown you. I will try to make time at the end to show you some stuff. I apologize if people are hoping this would be a Wrightsoft training, but those trainings are 2 days long. I get 2 hours. So unless you, and the 2-day training, people say it's like drinking from the fire hose. Yeah, 2 hours would be, I don't even know what. So here's a little one. I learned this. I didn't know this. The only way I learned this is from my own home. I, like an idiot, bought a 100-year-old that's 98 years old, a 98-year-old house. And in Massachusetts, we have this very cool program called Mass Save that they'll basically pay you to insulate your house. And they'll give you a 0% interest loan for 7 years to replace the HVAC. It's pretty awesome, right? Yeah, it's
They call it Massachusetts.
yeah. Well, yeah. Actually, it's funded by the power companies. You all have programs like this. This is just what ours looks like. Right?
The
So,
people's money.
yeah, it's cool. Well, ours is Cool Smart. That's what it's that program, but
Yeah.
within it, it's mass save. And anyway, I bought the house. First thing we did, insulate it, air seal it, replace the HVAC, right? So it's 870 square feet. I never lived there, right? It's dumb of me to buy the house in the first place. At least I bought a small one. And after I was done replacing the windows, insulating it, air sealing it, etc., the load was a ton. I live in the Boston area. I live way outside of Boston these days. The house is outside of Boston. I live in Massachusetts. The load was 1 ton, right? And all due respect to my electrify everything people, this was before a 1 ton heat pump was available, and even if it was, my electric rate is 25 cents a kilowatt.
Oh, man.
No thanks. I'll electrify everything when, Move is right, actually. I can move 1 town over and it'd be 13 cents a kilowatt hour. Should have done my research, right? So I'm going to go furnace, I'm going to go air conditioner. And I know I'm going to have a moisture issue, right? I know moisture is going to be a problem. And hopefully this doesn't get to him, my contractor. But my contractor, in our area, contractors or at the time, this was 2-3 years ago, didn't feel that they could sell inverter technology, right? High electric equipment had something to do with that. And so even though I had found a contractor who wanted to work with me and wanted to have a relationship with the Wrightsoft guy, basically, and was going to take care of me, supposedly, I shouldn't have said supposedly, he took care of me. But he kind of refused to do the inverter technology. He's like, I've never done one, and I'm going to be honest with you, this is going to cost me money in the long run. I'll be back to your house. We've never done one. We're going to be back here. So we're going to charge you like $5 or $6 grand more if you want to go inverter. On a 2-ton. And I was like, I wanted to brag about inverter technology. I wanted to be able to tell my classes I had one. I just didn't want it that much. So we started looking at other options. And his suggestion was like, well, let's go 2-stage. 2-stage is cheap. It's only, I'll charge $1,000 more. Nothing. And I said, cool, let's look at the numbers. Because look it up. Because 2-stage should, in theory, help my moisture removal, right?
In theory.
Nope.
That's what they say.
Nope. This is a chart that I got from Copeland Scroll. Now, I'm not throwing shade at Copeland here, right? This is how most of these products work. And this is also improving here. So this is the nominal, and we all know what nominal is, it's useless, but this is the nominal high and low stage. So you can't read that from back there, can you? How about now? So the 5-ton, right, or 4-ton, if I could look at all these, right, the high and the low, the relationship between it is all of these above 2-ton are somewhere between 100 and between 62 and 67%. Right? Low stage is like 62 to 67%. This is an inverter. This is just a scroll compressor. But the 2-ton low stage is 78%. The 2-ton low stage was bigger than a 1.5 ton. And low stage is not the efficient stage, right? Low stage, you don't, and this was in somebody else's meeting, I forget whose, I'm sorry, but you don't do 2-stage for cost savings, right? You do it for comfort, okay? Low stage would have created a larger moisture problem in my home than a 1.5 ton. Now, this is a sweet spot, right? This is a one-off. And by the way, while I was looking this up, Copeland also, when I was looking up some of the newer product lines, like from the brand, I'm not telling you what brand went in my house, but from the brand that went in my house, the 2-stage now drops down to like 70%. It used to be 85, by the way. It was the 2-ton was like 20,000 BTUs at low stage. Now it's down to like around 18. Actually, it's just around 18. So it's about a 1.5, right? At least it's not worse than the 1.5. Although remember, low stage is not the efficient stage. So a 2-stage would have been a terrible idea. What I end up getting is a single-stage outdoor unit, 2-stage variable speed fan with a smart control that when it senses humidity overcools the space on a low fan speed. It's never above 55% humidity in that house. Unless it's 85 degrees and raining, in which case, lower your expectations, homeowner. So, yeah. So we heard, and the point of this, by the way, because maybe this goes away as an industry problem. The point of this is not like, ooh, I better not use two-stage 2-ton units in these situations. Although that wouldn't be a terrible takeaway. The takeaway is look it up, because tomorrow it's going to be different, right? Or next week is going to be different, or next year it's going to be different, right? If you're someone who always looks it up, you don't get bit in the rear end by this stuff, right? So, you knew we were going to talk about rule of thumb here, right? I'm the Wrightsoft guy. So we all have apparently the same slide, the three of us here. Mine's this one, right? This is the one where you cut the holes out and you stand at the front of the house, and if it fits in the thing, yeah. And by the way, I didn't speak up because I spoke up enough, but the craziest square feet per ton that I've ever heard is 350. Everybody was shocked by 400 in this room. I know a lot of 350. Then again, that's like Arizona. So, or you can take the age of the home divided by the climate zone and multiply by the square feet of the floor area and add the number of windows, except on Tuesdays. So here, this is going to get a little mathy, not too crazy. I won't actually use too many numbers, but he doesn't go through the floor. I mean, it does, but not slabs, right? And even over crawl spaces and basements, you don't get a lot of heat. What temperature is it under there, right? I mean, it's not that bad, right? Heat goes through walls, particularly in cold climates. Heat goes through windows everywhere, and ceiling ducts and infiltration is kind of an everywhere thing too, right? So it's the surface area of the building, not the square footage of the floor, okay? Now I'm going to try to make this as simple as I can. So this is what mathematicians call the cube square problem, right, or a square cube problem, whatever. If I had a shape that was a 1 foot by 1 foot by 1 foot cube, and I calculated the surface area of it, each surface would be 1 square foot. So the total square footage of that 1 square foot cube is 6 square feet, which creates a ratio or a relationship for every 1 square foot. There's 6 square feet of surface area, which is what the heat actually goes through. 1 to 6. If I make this building 5 feet on its side, right, and it's not true cube square because I'm not making it 5 feet tall, we'll keep it 1 foot tall because that's how houses work, right? So each wall would be 5 square feet, the ceiling would be 25, and the floor would be 25. That's a total of 70. But the ratio for every square foot of that shape is under 3 square feet of surface area. So for that shape and that shape, I have twice as much surface area here as I have here. Okay, let's think about it different because some people hate math.
Can you back up there?
Yeah, absolutely.
The internal squares are on a heat load.
Hold on, yeah. So for the people who I don't like this math and graph crap.
No, I like it. I just didn't understand.
Well, think about this then. Picture a 2-ton house. I don't care how big you make it, okay? Whatever you think a typical 2-ton, let's pretend you did a load and did one last week and you know what one looks like. I've been to a 2-ton house, but you got to make it a rectangle for me, okay? Picture it in your head, a 2-ton house. Okay, now picture 4 of them on a grid like this, okay? Now, we're going to think of being far apart enough that they're not shading each other, so they're all still 2-ton houses. If I did that, they wouldn't fit in the slide. Now what I want you to do is I want you to take that picture, I want you to smush them together and make one big house. That's a 5-ton house, not an 8-ton house. 2 of the outside walls just disappeared. Right?
I think
all the load from the windows, all the load from those walls, they're gone.
When you mean surface area, I think what he's missing is you mean exterior.
Surface walls, ceilings, floors.
That way,
right?
Interior.
But yeah, it helps with this picture. Right? I forgot Ty's last name. Brenneman, thank you. Did a presentation about teaching in here, and I managed to keep my mouth shut during that one, ironically, and. To summarize one of his points, a good way to teach is throw it against the wall and see what sticks. So that's why I do it a couple of different ways. So this one has been very well handled already. I don't think we'll be spending too much time on it. But again, I want to just try it thought experiment-wise because I think we got a little stuck. Sometimes we get a little too out in the field in our heads. One of the things you got to realize when you're designing a system is you get to pin certain variables. You're deciding ahead of time. It's not like you're going out and this is what you got and you're dealing with it in service. There is a difference, right? Because when we talk about the velocity in the duct having something to do with the velocity in the register, you're thinking, this is the duct in the register. If I slow the air down in the duct, it's going to slow down when it comes out of the register. And that's absolutely true. Because in the field, you haven't decided how much air is supposed to come out of that. Okay? But let's change it. Let's change our field perspective here for a second. Okay? Let's just take the world's simplest duct system. 2 ducts. Okay? I got a 6-inch takeoff over here. I got an 8-inch takeoff over here. I want both of them to have 100 CFM, and both grills are the same size. Now, if I put that in, I'm not going to get 100 CFM out of both of them, am I? What if I put a damper at the takeoff for the 8-inch run? Put my flow hood on that register and started to adjust until I got 100 CFM out of both of these. What's the velocity coming out of those 2 registers now? Is it going to be different? It's 100 CFM coming out of that, and it's 100 CFM coming out of that. The area of the grill hasn't changed. If there is actually 100 CFM coming out, it must be coming out at the same speed, because it's coming out of the same size grill, right? But what everybody thinks is they're not comparing it like this. They're comparing, in their heads, they're comparing the 8-inch before you close the damper to the 8-inch after you close the damper. That would be insane, right? You close the damper, you're going to get less air out. Duh. We're not comparing those things. We're comparing the 6 to a dampered 8. In that situation, you're going to get the same air out. And when you're designing, you get to decide whether or not, you get to decide whether you're going to use a 6 or an 8, right? It's going to be determined by what size filter you use, or what coil matchup you use, or what speed taps you use, so you get to make those decisions. So you first decide, this is what I mean by pinning a variable. You first decide, okay, here, look, this right here, I'm going to put I need an 8-inch duct for 100 CFM. Cool. And because of all the friction that happens, going through there, that'll be the case because you did the math. Then you're going to get 100 CFM out of that. Whatever size grill you put on it, it's going to have 100 CFM coming through it. That's just how it works. And again, there's going to be time to circle back to that. So, I do want to recommend, we were talking through lunch, and I think I recommended to 4 people the mean radiant temperature article. This is a slightly different way of thinking about it. And by the way, thermostat location. This is my favorite. If I really want to annoy a class with my, nothing you were ever taught is ever right, which is not true. But it feels that way sometimes. And if I feel like somebody needs to have that experience, I will ask them, where should you put the thermostat? Because what you were taught was to put it in the hallway. So there's some rules, there's some do's and don'ts in the manual. I can't remember ZR or T now. Manual ZR is the zoning manual. Manual T is the terminal placement manual. And I can't remember which one has the thermostat placement rules in it. But I think it's ZR. But the rules are this. There's 4 don'ts, and we know the first 3. It's the 4th one that gets us. The first one is don't put it on an outside wall. Right? Duh. Second one is don't put it in a beam of sunlight. Yep. Right? The third one is don't put it directly in the flow of a supply air.
Yeah, what's number 4?
Number 4 is don't put it in the hallway. Okay. Number 4 is don't put it in the hallway. Right? When was the last time you all hung out in the hallway?
Yeah, right? That's a good
right?
point.
Yeah.
College.
So, you got a couch in the hallway? How big is the hallway?
College.
Oh, college.
So many people in the house.
Yeah, college. This is another one of those rules that's probably become a little less important the better we build a house, right? Because it does go back to mean radiant temperature, right? The colder the outside surface of the building is, or the hotter the outside surface of the building is, the more this will be pronounced. But I want you to think of heat like an invading force, right? And this little stick figure is my customer's favorite spot. This is the Sheldon spot. You're in my spot, okay? This is where I go right here, okay? And heat is coming in the house. It's a lot easier to think of it this way than on the cooling side. I mean, on the heating side. So heat's coming in the house, and here it is, and it's already here, right? And heat continues to come in the house, and look at how much heat is coming in the house by the time it makes it to the thermostat, right? Because radiance has a ton to do with actual comfort, right? Oh, sure, yeah, the return air is going to be pulling back some of that air, and it's, you're going to get that air. First of all, returns don't suck, right? The thing where you put the hand in front of your face and blow and then suck. The way I always saw that was with a lighter. Now, I quit smoking, so I don't have a lighter anymore. But you can put a lighter out to here and blow it out. You can't suck it out, right? So you do get some of that residual airflow, but remember, I was sitting on the patio at a restaurant where the air was 60-something degrees, and it felt warm because I was underneath radiant heat lamps, right? Radiance has a lot to do with comfort, and the further away I put that thermostat from my livable space, the more likely I am to have that temperature swing.
Yeah, so 60% is radiance.
60%, okay.
More than half.
Yeah.
So if you're missing heat radiance, you're literally missing more than half the equation.
There you go. Right?
What's he saying?
60% of the comfort experience is radiance versus air temperature. So, here's one. So you have a duct, and this is similar to another slide. You have a duct, it starts off 8-inch, squeezes down. PowerPoint didn't, I should have done this in Wrightsoft and copied and pasted it, but I literally thought of this slide while watching Allison's presentation. I was like, oh, I got to add that. You got a duct, it reduces down to 6-inch, and then it increases back up to 8-inch. How much air do you get out of that? Remember, trick questions.
Whatever you want.
So that's a good answer. I like that answer. But is it the equivalent of a 6? Is it the equivalent of an 8? So a lot of people think that's going to be the equivalent of a 6. It's not. It's also not the equivalent of an 8. Right? It's probably somewhere in between if these are nice long runs. Probably. Okay? And it's because it's not about the size of the orifice, it's about the friction. Right? And so when it reduces down, that causes friction. And when it runs through just a little bit of 6-inch duct, that's some friction right there. Right? And when it increases back out, there's some actually more friction because it's just changing shape. But compared to running through all of that squeeze from that 6-inch duct, depending on how long that is, that's going to be more friction than just that little bit. Okay? Or could be. It depends on the length of that reducer, the angle of that reducer. It depends on a lot of factors. Right? Which is why, if we talk about it now, well, now this could be worse than both of these. You could get less air out of that than a straight 8. You can get less air out of that than a straight 6. Because there's more friction from those fittings than there is in a short length of 6-inch duct. Because it's not about the size of the duct, it's about the amount of friction you create.
So you're allowed one pinch point in your...
No, you jerk. No, but it's not, and it has to do with how that pinch point where it's sloped over the rafter or whatever.
You get one.
Yeah, no, you don't get one of those.
I got a question.
Yeah.
Let's say in a weird situation you have an install and everybody puts balance of dampers at the plenum.
Yeah.
But let's say you have a drop where the balance of damper is like, let's say it's a 30-foot run and there's a balancing damper going to another distribution box, but you couldn't get the balancing damper at the plenum, but it's at the entry of the distribution box. Does that work for cutting it down?
So,
or does it have to be
for proper balancing, your best bet? So I once worked with a contractor in Austin. Actually, they went out of, maybe you can. I can't remember the name of the damn contractor, but they went out of business because their comptroller stole a couple $1 million from them. They used to do production work. They used to do a lot of installs, and they decided. And in Austin, you have to pass an air balancing test, right? It's like 15% of 15% in city limits. And they decided that balancing was costing them too much time and money, and so they wanted to do an install without balancing the system. Okay. So they decided they needed to use Wrightsoft, they needed to use variable friction rates, they needed to use this, they needed to use that. And one of the things that they decided they needed to use was anytime they used the junction box. So they had a lot of rules to make it happen. And one of them was never have more than one Y in series, right? So they split once, but the higher airflow would always be the straight side of the Y. Right, so they're ordering special Ys, and anytime they used a junction box, they did a properly designed junction box. Right, for some of those who lives in an area, I'm not asking who uses them because I think people won't raise their hand. Who lives in an area where you see a lot of triangle boxes and junction boxes? Well, that's almost everybody. So, junction box, not exactly optimal design. Right, optimal design would look more like a round sheet metal trunk with some black branches, but If the 80-20 rule, that 20% better is going to get me 80% of the results, stop using triangles. Okay? So there's a section in the Manual D about junction boxes. Triangle boxes are bad, and I'm not going to end it there, for a couple of reasons. One, air in a flex duct can pick up spin. Air moving through a flex duct, because that helix, right, going around the edge, that air starts rubbing up against it, it starts rolling, right? And that rolling air rubs up against this air, and it starts rolling. And the next thing you know, the air is sort of spinning, spiraling through the duct, right? Spiral duct. Not different kind of spiral. So this is spiraling through the duct. And when it comes into the triangle, I want you to think of the shape of a triangle. As that air rolls over, it hits one side. And that air can dump onto one side and start the other. Now you want to know the fun part? The fan turns off and it starts up again, the spin can change directions. Turn the fan off and turn it off and you turn it on again, it didn't spin this time. There's turbulence, right? There's a lot of stuff going on there, right? We think of it as like one flow, right? We know when you take velocity pressures, you have to do transverse, right? You have to take this measurement, this measurement, this measurement, this measurement, because air's going all kinds of crazy. So when it does, it can pick up a different spin. And those triangle boxes are terrible. A quote-unquote good junction box, and, right, we can all kind of that. I'd rather see a Y or Y's plural every day of the week. But a quote-unquote good junction box is rectangular in shape, does not have a takeoff off the end of the box, has two widths of the intake. You got 10 inch coming into it, you got to go 20 inches before your first takeoff off the side. And here's the cool thing about this. And there's a lot of nerds in here. I know you're here. For the nerdy among us, one of the more annoying things in the quote-unquote scientific community, not as annoying as paid science, aka bullshit science, but second only to paid science, in my opinion, is lack of reproduction in studies, right? Because nobody wants to be the guy who just did, I don't want to be the guy that did his experiment, right? What's the fun in that? I don't get any credit. Like, yep, you were right, nice job. And, I'm a footnote and nobody cares and I don't get I don't get my contract renewed or whatever, right? This junction box design was actually a verified study. Hank Rotowski put it out there that you should also have a diffuser coming into the thing at the intake. And Texas A&M reproduced the results, but found that the diffuser didn't make any difference. Right? But it's a miracle. It's been studied twice, and we came up with the same results. So, having said that, you should ideally balance at the branch somehow.
Didn't that same study say something to the effect of it really didn't make any difference if there were dampers in it also? Because I have one from 2009, I think it was, and that's...
I don't think so. It might not have... Dampers don't generally affect total airflow, because if you test total airflow, they should be open. Putting the damper in the right place, though, it tells you where the controls should be, right? So depending on what they were testing, I can't imagine a situation where Manual D said anything other than you should have balancing dampers.
Oh, it wasn't Manual D.
Yeah.
But was the group that studied.
They may have studied, and that's right, because an open damper should be very low restriction. So if they were testing total airflow, that makes sense, right? But there is no question it's going to reduce your ability to control airflow. Without a damper, without a damper, you're stuck with wrapping a conduit strap around it and tightening it up until you get not enough airflow out of it, in which we don't want to do that. Right. Yeah. That's bad. Yeah.
You get one pitch.
Yeah, stop it. People remember stuff like that.
All right, so to follow up on his question. So his question was, correct me if I'm wrong. Can you put the damper at the intake of the triangle? You said don't use the triangle.
I mean, yeah. So putting the damper at the intake of the triangle is going to create more turbulence.
No. Hold on. No, I'm not saying we're not using triangle.
Oh, at the intake of the junction box.
Yeah,
it would create more turbulence, but I don't know is the answer to that question.
Yeah,
So
right?
tell our duct
guys. I straight up don't know. I can
triangle.
tell you it's better to put it at the branch because it gives you remote control. If they were all feeding the same size run with the same amount of air, which when is that ever going to be the case? But if it was, maybe that would be all right. But that one's going under. I don't know, guys.
Is this study that explains
Good junction box design, yeah.
Is this available like online, like Google or whatever?
It's in the manual D.
In the manual.
In the manual D, in the back of the book. So past the standard. Manual D is like yay thick. I'll tell you what. I'm pretty good at digging up the pages in the manual D and emailing you what page to look at. So send me an email and I will send you. Actually, that's a page I've emailed so many people. I might actually have it photocopied on my computer. But send me an email and I'll send you the specs on that.
What would you say is better, or does it make a difference if your damper? You said put the dampers in the branch rooms.
Yes.
Does it matter where in that branch room the damper is?
Do the homeowners care about how loud it's going to be? Right. Any obstruction is going to create restriction. That's going to give you control over airflow. But there are other considerations in designing a duct system. So, okay. How much external static pressure? Another one of these trick questions. How much external static pressure does your average fan have? Look it up. Yeah, I'm going to save you the trouble on that one. So, I love this. They still sell this. I think they're phasing it out, and I'll be sad to see it go in a way. I will not actually be sad to see it go, because some poor homeowners getting this stuck in their house, and some poor contractors using the damn thing. This is a brand list. I put it into an Excel spreadsheet so you couldn't even recognize the damn format. I renamed the speeds so that you can't tell. No, maybe, not saying. So, baseline fan power isn't always 0.5. I'll give you one no. We're not playing the guessing game, but that's a no. They are sponsoring the event. It's definitely not. So, and I wouldn't just say that if, you know. I really wouldn't. There's a few people in here who know me. Go ask them. So, when I look at 2 ton, now remember that blower housing size, right? The actual velocity coming out of the thing? When I look at 2 ton, and if I'm looking for 400 CFM per ton, and I don't care what you're looking for. If you're looking for 350, you're just going to shift the same amount over to the left. It's not going to matter. So if I'm looking for 400 CFM per ton, that's medium high speed 0.5 at 2 ton. Or if I go high speed, it's somewhere between 0.7 and 0.8. The same family, the same brand, the same everything. We just changed tonnage. And if I use Speed Tap 3 for 1200 CFM at 3 ton, I have to have no more than 0.2 inches of static on this fan. And if I go to high speed, between 0.5 and 0.6.
Which means you can't use it.
I could use it on high, right?
Yeah.
That's what it means. It means this fan has to be set on high to get the airflow it needs.
Yeah.
But it might mean I can't use the 5 ton. Because at 5 ton, to get 2,000 CFM of air, I can put no more than 0.1 inches of static on that. That's all together, right? That's the, and I shouldn't abbreviate like that. I'm a teacher, I know better. It's static pressure loss or friction. That's the coil, that's the filter, that's the ducts, that's the dampers, that's the grills, that's everything. 0.1. No way on earth, right? At Speed Tap 4, 0.4, not on a 5 ton. This is a different brand, but the pressure loss on a 5 ton when it's wet could be 0.4. That's a 0.397. So how much pressure loss is there in a coil? Look it up, right? Because at 2 tons, we're looking at between 0.14, maybe even a 0.04 if we're using the 2 ton coil on the 1.5 ton, airflow, or all the way up to 0.08 for the larger coil. All the way up to 0.4, even within the 2 ton range though, right? If I use 800 CFM, it's 0.23 on the smaller coil. Like it's all over the map, right? By the way, and again, I'm going to try not to name names, but there's certain manufacturers who thump their chest and are very proud of how good they are at moisture removal, and good for them. Because you know what? I'd rather have a system that was better at moisture removal because I can design around this. But the ones who have the best moisture removal tend to have the highest pressure losses on their coils. Yeah, they kind of go together. And I'm not adept. Stop it. I'm not an adept enough engineer. So with that brand, it actually their bottom of the line stuff, their builder's grade stuff, might as well be made by a different manufacturer. Right? There's some certain manufacturers are large enough. They're not a monolith. They're not a monolith. you can't like say one thing about this manufacturer. But it's something you have to keep an eye on, because you can go from one manufacturer to another, and the quote unquote rule of thumb for how much pressure drop you get from a coil changes just because the style of coil changes. Oh, and by the way, third party coil manufacturers, I was doing a job last week where we were looking up their real units, and the amount of times we said to ourselves, that can't be right. The pressure drop on like a 3-ton was 0.4, right? Yeah, like they were giant slab coils, and it's a whole thing. But yeah, so and like I said, don't get me started on filters. So here's the thing: I'm looking at time, and I'm going to skip these. And the reason I'm going to skip these, it looks like I'm skipping the whole thing, is I have a whole other presentation that has that stuff in there, and we're going to do that. And so for some of you, this is remediation. For others, for those of us who are always, because I got to tell you, man, I taught this for 12 years before I had that aha moment where I understood the whole static pressure thing, right? 12 solid, like I was teaching the right process. You can have the manual D in front of you and do the steps and do a good design. You don't literally need to understand all of the physics, right? That's nice. So wouldn't it be nice if you understood what you were doing, right? So it took me a long time, and there was points in there where I thought I had it, and not so much. So you've seen that. We'll spare you. Pressure. Oh, man. Oh, wow. Oh, sorry. Thank you.
A little bit before you move on.
Yes, absolutely.
Static pressure. When you're talking about that baseline, are you referring to the rating that they have for that cabinet?
Yes, I'm referring to the fan chart, which you should always go to.
Right. But what I found is that you can have a fan chart that gives you those,
Yep.
but the cabinet rating on the front of the sticker is lower.
Yes.
So is that like the nominal for like
It's
$6 or something?
it's worse than nominal. It's like the don't sue us. We put this on the nameplates. And they're like,
The reason I say that is because I made a mistake, and I would look at the chart, and I would say, okay, this fits static pressure that I've measured to do this replacement, that kind of thing. But when I would buy the air handler, going to put it in, I have 0.2, 0.3, and I noticed they're louder. And I realized that I had to move up to a different air handler.
yeah,
$400, $600 more, depending on the tonnage.
Yep.
More expensive. And funny enough, that.
but you're lowering velocity, right? So the first one might have been getting the airflow, but because it was getting the airflow through that cabinet, it was louder, right? We all know the manufacturer I'm about to talk about, but there's a manufacturer who's has a claim to fame. They have several, but one of them is that we make the smallest cabinet in the market, right? We're the smallest air handler in the market, right? And actually, it's one of the things that I will sometimes reference in a class, because if you use that unit and you compare it to the Carrier Infinity or the Hyperion or the Dave Lennox Signature Series, or pick your one, pick Affinity, whatever, and you put the same ductwork on it, you'd have to be insane to expect the same airflow out of it, right? And there's constant sacrifice when you engineer and design things. You do it, and so do the engineers at the manufacturers, right? We wanted this thing to be compact enough to fit through that tiny scuttle hole because we wanted that niche in the marketplace. It's going to be loud, but you know what? It's that or a crane, and this homeowner can't afford that, and so we're going to sell this thing, right? And always looking it up allows you to sort of understand what some of those trade-offs are. So I, as a somewhat outsider in the industry, I'll drop this bomb on you. This will be fun. Okay, so I did not start with an introduction of me. I don't want this to be about me and, I'm so great. Because I got too late. Yeah, thank you. Because I've got a degree. Before I started working for Wrightsoft 17 years ago, I was telling some folks last night, I didn't have a single year where I didn't have at least 2 W-2s. Because I got a you want fries with that degree. I've got a degree in English communications and philosophy from a liberal arts college. I've had a subscription to Popular Mechanics that's way before Wrightsoft. That counts for something, but just barely. Now, I am EPIC certified, and I've lived, eaten, sleep, and breathe HVAC design. But man, to what degree I feel like I'm good at this job is because I knew I wanted it. I wanted to be a teacher back in the day, and turns out I hate children. And so
Nothing's changed.
And so I found a way to be a teacher and said, I want to do that. And so, I tried to learn the HVAC industry by getting contractors to teach it to me. So I learned beer can cold and 400 CFM per ton and 400 square feet per ton and all the crap. And I thought they were right. I mean, like, these guys are the professionals. They should know. And then I had to unlearn all this crap. And the way people talk in the HVAC industry, you would think pressure is the enemy. Pressure's not the enemy. Pressure's the one doing all the work. Right? The only reason things move is a difference in pressure, high pressure and low pressure. Right? Pressure is not the enemy. I have too much pressure, not a thing. Right? I mean, possibly a thing could get loud, but it's generally not a thing. Pressure is the thing doing the work. Friction, and this is stuff that's been covered, but friction is the thing that's pushing against it. Right? And you can split hairs and call friction turbulence and friction, it's friction, right? If Wall Street can call inefficiencies in a market friction, then I can call turbulence friction. Everything that causes something to not happen that I intend, that's friction. Okay? I intend air to move. What's stopping me? Friction. Okay? So when we talk about pressure, it's just another way of saying energy, right? So when the fan blade spins, it imparts energy. And I'm not going to take this like kinetic and potential and all this crap. There's energy there, though, right? You play pool, you hit a slide ahead of myself. If you're playing pool and you knock the cue ball into the 8-ball, that 8-ball does not have the option of sitting there on the table and staring at it, right? Once you've imparted energy, it has to be used, right? And so with duct work, there's two ways of using energy, right? And we talked about this a little bit. There's velocity pressure. That's hold on. That's this, right? That's the air going through the duct. And then there's static pressure, which this is comparable, but don't look at this. Forget this. Look at this thing. Look at this thing. Static pressure. That's static right there. Okay? So velocity and static, right? And I like my little visual aid, and because I don't love that picture. And they're always in balance. And this is the key to understanding the whole damn thing. And engineers, no offense to engineers, but they often say to me, pressure is always equal. Like, I tried to learn this from the really smart guys at Wrightsoft. They're like, oh, pressure is always equal. And in my head, all I kept thinking was, no, it's not. It's different here, and different here, and different here. That's not what they meant. Okay? What they mean is, at any given point, this will be my duct. No, I guess I can't do that. Any point along the duct, at that point, you have to use all the energy that's there. So if you're using it for velocity, you're not using it for static. If you're using it for static, you're not using it for velocity. And Nate in the back of the room threatened to buy me a suit of this guy because it's ridiculous that I use this in a presentation so often, but it's my favorite way. I was talking to Ty yesterday about how addictive it is to watch people's eyes go, oh, when you teach them something. And this causes a lot of that. This is the best demonstration of static pressure and velocity pressure in action you'll ever see. When it starts off, it's folded over, and when you turn the fan on, it slowly starts to stand up because air has nowhere to go. There's no velocity. Doesn't have anywhere to go. So how does it use its energy? It uses it for static. It pushes out. And as it pushes out, it starts to stand up, gives it a structure. But the second it works that fold up to the top and air can go somewhere, the air starts going, velocity rises, static falls instantly, and it falls over, and the cycle repeats because it's always in balance. Okay? So, if friction is the enemy, it'd be really nice if we could measure friction. It really would. Because this is what we're trying to manage. That's what duct design is, managing friction, right? Unfortunately, there's no such device as a frictionometer. Right? We don't have a little robot that we could drive through the duct and be like, here's how much friction it is, right? That's not a thing. But we can measure static. So the question earlier today, why don't we use 1 foot instead of 100 feet? I have a guess that's a little bit different. It's arbitrary is the right answer, but I have a guess. So much of what we do in the HVAC industry is determined by our tools. What's up, tool manufacturers?
Absolutely.
You are leading the industry in so many ways that it's ridiculous. Right? I don't have a way of measuring directly friction, but I have a way, and so I think it would have been really difficult to have tools that had a tolerance level that could detect how much friction there was in a foot of duct. Right? I think if I had 100, and it would be weird to use 4, right? So they went, in 10 feet. Maybe I still am not within the tolerance of my tools. I'll bet you 100 feet was Willis Carrier going, I need this much before I can trust this device. It's a total guess, but that's my guess. Because we talk way too much about static pressure in this industry when what we're really worried about is air moving. If you ask me, I'm an outsider. But I want air to move. What do I care about static? You ever seen a duct system explode? You know what engineers are worried about static pressure? Right? Hydraulics engineers, right? They screw it up and it blows up, right? You don't see too many duct systems exploding, right? But velocity pressure is a pain in the butt. Oh, actually, I've probably got a tool guy in here who's like, no, it's not. You got to use our tool. But in general, up until, somebody invents the new cool thing, velocity pressure is hard to measure, right? You have to take that transverse. Right? You have to take a bunch of different measurements. And air is weird, man. It's moving faster on the inside than it is on the outside, and I got to do this and average them all together, and screw that. I can just test static pressure, because what do we know about static and velocity? If static is high, velocity is low. So I just test the static, and I can infer the rest, right? And that's why we talk so much about static. It's the easier measurement. I have tools that do that, right? And so when we talk about airflow, and there's our conservation formula here, if 100 CFM goes into a duct, 100 CFM comes out, right? If there's no leaks. Now, I'm not going to change size. We're going to say that there's no size change in here. But if at the point where 100 CFM is going through at the very beginning, if the duct is the same size on the very end, the average velocity at that point is going to be the same, right? Same amount of air. Same velocity if the size doesn't change, right? Average velocity across the track. Okay, so that means that when I run my ductwork through all these fittings and all this length of duct, that I don't lose any velocity. I don't lose any velocity pressure. But I thought these were bad and these were worse, and all that duct is not so good for airflow. Well, they're not. You lose energy. You lose energy by losing, let me get a little out of myself here. You lose it to static. The velocity doesn't change, but you have less total energy. You lost it all in static. And so when we say static pressure loss, that's our way of saying friction. Static pressure loss is friction, right? And I'm guilty of it. Literally everybody's guilty of it. We just say, oh, the static pressure on that. The static pressure on the fan, the static pressure on the filter, the static pressure on this. It's no wonder we're always confused. Static pressure loss has nothing to do with the pressure. It has to do with the friction. It's the amount of friction created between point A and point B. It's the amount of energy lost between point A and point B. That's the amount of friction between point A and point B. And it just so happens it's all going to be on static if you don't change the duct size.
Oh man, always told me drag. It was just a creative
Drag?
word that was because it drags you down.
Yep, and drag has a lot to do with the turbulence going through there. You get the the Venturi effect and the cause of the swirl, and you get all.
He was a NASCAR fan, man.
Yeah, also, yeah.
Right.
Yeah. Know where I am, right? I should stick with that. I like drag. Yeah. So when you talk about static pressure loss, you're just finding a different way to say friction, right? And so when we're talking about or arguing about the amount of resistance in a fitting, what we're talking about is static pressure loss, right? In fact, we'll get to that. But see, that's why we use this thing. And that's why, and by the way, the guys who taught me who weren't doing this right told me that it's per 100 feet. And I wanted to ask them, well, why? Is every duct system you do 100 foot? Something in the back of my brain was like, don't ask them this question. That's not gonna go well. Nobody could tell me why the per 100 feet was relevant, right? Because we don't always use 100 feet of duct. Like, why do we use 0.1 on the ductulator? Why did somebody teach you to use 0.1 on the ductulator? That's the thing, man. Like, you probably paid somebody money to have them teach you to do it this way, and it's not right. And it's because, in my opinion, residential duct design is backwards. Okay? It's the whole theme of this whole thing. In commercial duct design, you start with that friction rate. You start with 0.1. Right? Now, we're talking old school commercial duct design. There's more math, a lot more math you can do. But if we're talking old school commercial duct design, you'd start with point 1. You design your system, and then you would pick your fan or configure your fan. Residential duct design doesn't work that way. This is my fan. I don't get to change it, right? Sometimes you do, but not often. And if you're not going to change anything, it's not going to work. You got to change something, right? You got to adjust something to make it work, right? Yeah, okay, we get some fan speeds. You have enough? You have a high enough one? In commercial, you just go get a bigger one. Use a high static blower. Change the pulleys.
Change the coil.
We have a little control over that in residential too.
Coil fins.
Coil fins, yeah. So look, the commercial duct design process, you'd start with point 1 or 0.08. And point 1, by the way, it's the Goldilocks, man. Right? Air is going fast enough that you're being economical, you're not using too much duct work. It's going slow enough that it doesn't sound like a jet engine, like it's a sweet spot. And so you use point 1, you lay the duct system out, and you say, these are going to be my sizes. Thou shalt be 6-inch. That's it. Okay? And so then what you would do is you'd measure the length of that duct. You'd say, okay, well, here's the furthest return, and it's going to go this far, and this is going to go this far, and this is going to go through the unit, it's going to go over here, blah, 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 blah. How many feet is that? So it's 120 feet. Well, if it's 0.1 inches of friction, pressure lost for every 100 feet, and you're going to go 120 feet, you're going to lose 0.12 inches of friction, right? Get that? 0.1 for the first 100 feet, 0.02 for the next 20. And then you would take that number and you'd do a crazy thing. You'd write it down, right? And then you would go look up the coil, assuming it wasn't an air handler with a coil included in the rating, and you find out what pressure loss was there, because the ducts and the fittings are not the only thing that creates resistance. You get that too. So you write that down. And then you figure out the filter, and you write that down. And you take your grills, and you write those down, and the dampers, and the fittings. The fittings have pressure loss, right? And this is partly what I think where we're having an argument, because there's a commercial method for determining pressure loss in fittings. And the residential method is it's 90 feet, right? So what that is, by the way, because we all, well, maybe not all of us, but many of us are familiar with equivalent feet. Okay, here's what equivalent feet is. It's really not that tough, okay? If you assume 0.08 is the industry standard, right, and that's, that's debatable, but who cares? Hank Rotowski decided it's 0.08, so there you go. So if 0.08 is the industry standard, and you have a fitting that at 900 feet per minute creates 0.08 inches of pressure loss, that's a 100-foot fitting. It's the same amount of pressure loss. If you have a fitting that creates 0.04 inches of pressure loss, it's a 50-foot fitting. If it's 0.02 inches of pressure loss, it's a 25-foot fitting, and so on. You're literally just saying pressure loss. You're just doing a conversion using fixed data points, which is why getting away from the recommended friction rates of the Manual D becomes problematic, because they said this friction rate and this velocity, and the further you get away from that, the more the assumptions start to break down. But they're saying at 0.08 with 900 feet per minute, this is the pressure loss of this fitting, and it would be the equivalent of this many feet of duct. Okay? So, you take all those numbers, you add them all up in a commercial design, and that number down there at the bottom, that's how much resistance, that's how much friction your fan has to overcome. Go get one. Go find one that can do that, right? Figure it out, set it up, that's what you got to do, right? Residential goes exactly the opposite direction, okay? This is the fan I have, this is what it can handle. You got to look it up, we saw that slide already. It's all over the map. But once you know what you're dealing with, you can start with that number. Then you subtract the things that are not your duct system. This is just, math people and science people, they just call this isolating the variables, right? Just like, well, we don't want to have to do the math on all this crap, so if my fan can handle this, and my coils are going to create this much pressure, and filters are going to do this, and this, and this, and this, you subtract all that away, and what you're left with is called the available static pressure. It's what's available to the ductwork and the fittings, right? And so now your job is to, and I want you to pretend you don't have to do math. I want you to pretend you just have a little slide bar that creates bigger ducts and smaller ducts. And your job, and it is a slide bar, isn't it? You've seen some of those ductulators. Some of them slide. You just slide it until you create that much friction. And you hit that spot, you have created exactly enough friction to cause the right amount of air to come out of your fan. That's why you need to design the system before you know what number is on the ductulator. If you could change your fan, and some of you can to a degree, but if you could change your fan, you could be like, I'm going to design this duct system, then I'm going to go figure out what fan I want, and I have all these fan options everywhere from 0.1 all the way up to an inch of static. And I know they make them that can handle an inch of static. They're called variable speed fans, and you'll murder them putting an inch of static on them. So I don't have that many options. I am confined to my choices. And because I'm confined to my choices, if you do it that way, if you say, these are the duct sizes I'm going to use, most of the time you would end up being like, and my system doesn't work. Because I don't have the ability to create that much power. Right? External static pressure of the fan, power, energy. I don't have that much energy. I can't do it. I'm either going to have to pick a different fan, which means I'm going to resell this job, or I must change something. And by the way, you don't have to just change the duct size, right? You could sell a different filter. You could use a big-ass return drop and create a filter pressure drop that, with the velocity as low as it is a tenth of what it was what it was before. That's a way to get your ducts down to a regular size. But you're going to have to control something, right? And the traditional way of doing it, the manual D way of doing it, is figuring out what that pressure loss is. And by the way, the reason I didn't put the formula up on the board is I work for the software company. I don't want you doing math. I want you knowing what these numbers are so you know where to plug them in. We do math, right? That's why you buy software. We'll just move the slide bar for you, okay? Forget the formula. I mean, don't forget the formula. Formulas are nice, but they confuse some people. So I just want you to know why it is you're doing this. You change the size of the duct to make the fan work because you can't say this is the duct I want to use and change the fan instead. Okay? So, in case, because I have this sneaking suspicion that there might be a few folks sitting there going, I've been doing 0.1 for like forever. I don't have any airflow problems. I don't even know what this guy's talking about. So,
Test it.
what's that? Yeah.
Test it.
So, and test it is a good piece of advice. You should know, and it's why I brought up the topic this morning, that we do get a complaint from Wrightsoft Duct Design that the statics are too low if you follow our designs. Right? They're too low. That's not a problem. Right? Too high, that's a problem. Too low, that I can deal with. Right? And it's because of that thing we were talking about this morning, where these fitting equivalent lengths, they're kind of worst case. Right? It creates some wiggle room. So if you design at 0.7, you're going to go out and field and test it. It's going to be 0.6, 0.5, something like that. Also known as working. Right? So the thing is I'm of the opinion, again, strictly opinion, that 0.1 and 0.08 used to work. Anybody recognize? And you can read it. Anybody recognize that picture? Anybody ever done that? There we go. We got one. Yep, there's two. There's three, four. Look at that. That is a belt on a car built in the 70s that has been repaired, and not repaired, but at least, limping home with a pair of pantyhose tied around it. Okay. So, my father used to work at Raytheon, the big defense contractor. And he started out, he's kind of like me. I started off at Wrightsoft as a temp. If you're wondering how a guy with an English degree and a philosophy degree gets to do this, it's because they hired me to call customer service phone calls for 3 months as a temp gig, and I just wouldn't go away. He had a similar story. He started as a draftsman, but he ended up managing engineers. And he's got a lot of fun engineer jokes, and design engineers, people who work at manufacturing facilities. And one of them is ask an engineer what's 2 plus 2, and he'll tell you 4, but let's call it 5 to be safe. Engineers believe in wiggle room, right? When they design a product, they want it to work. Ask Jim Bergman. When they design a product, they want it to work in a range of conditions, right? They don't want you to have to stand on your 1 foot and hold your hand in the air and do it like this just to get it to work. They want it to work in all kinds of conditions, right? Wiggle room, safety factor, call it what you want, but we try to engineer things with that in mind, right? So, what happened to the auto industry in the 70s? Late 70s came along and we had CAFE standards, we had to start meeting efficiency requirements. And engineers don't want to get rid of the wiggle. When you're out there saying, why they put this, stupid control board here where I can't reach it and have to climb over the damn thing. Why don't they just, I can tell you why, right? Because the engineer didn't want to put it there. The engineer's boss came into his office and said, make it cheaper and better. Make it bigger and smaller, right? That's what they're doing. I need you to make this more efficient, and we need to not have it be more expensive. Yeah. Oh, okay, so I'll just make it better and cheaper then. Awesome. I should have thought of that before. That's what I wasn't doing before. Right? So they're going to have to take it out of somewhere. Where do they take it out of? They take it out of the wiggle room. Right? Stuff like point one on the ductulator used to work because stuff was just more bulletproof, man. You used to be able to fix it with a pair of pantyhose. Right? The wiggle room in this industry is disappearing. The standards that we have to hold ourselves are getting higher because the manufacturers can't make it cheaper and better, right? And so we don't have as much wiggle room as we used to, right? I think what happens a lot is, even on a newer system, is the system gets oversized and underducted, right? Point one works. Because I knew that load wasn't right. I knew it wasn't a 2.5. I put a 3 in, and I sized it at 0.1, and damn it if that didn't work.
But look at SHR on old equipment and now new equipment. And how fast you could remove moisture on an RC.
So here we go.
You know what I'm saying?
Oh, I know what you're saying.
I could pull
so he's saying, so look
minutes.
at moisture removal capabilities, right? He said SHR, but I like to just think of it as how good is it at removing moisture on an older unit and a newer unit. So number one, you can find new units that do a great job of removing moisture. You can find old units that sucked. But most people think that the trend has moved, especially on, shall we say, value lines of equipment. Nice way of saying that. We have sacrificed a lot of moisture removal capability. Now let me put my manufacturer engineering hat on. This is a product that they tell me we're marketing to the builders. Okay? What do we build now? Tight houses. What shouldn't I need a lot of then? Moisture removal. Cool. So the engineer does his level best, doesn't think he's doing a bad job, puts out a product that does this, right? And they hand it to the marketing department. Now, the marketing department is going to go out there and tell everybody when they shouldn't be using this thing, right? No, that's not the marketing department's job, right? And the TM, who knows all about the equipment, could take it down and put it back together, right? Yeah, I'm sure the TM can do that. No offense, TMs who can do that, by the way. They went to a half-an-hour class. They're an expert on this thing, right? And the half-an-hour class was taught by the marketing person. They're here to tell you what it's great at. They don't tell you what it sucks at, right? And now we have a homeowner who's got a tight budget. Now, they designed this thing to go into new construction, but hey, pretty please, can I buy this and sell it in the retrofit market? Yes, you can buy our product. Have as many of these as you want. And this is where we find ourselves. So it's not that all of our newer systems are going to be bad at removing moisture, but there are more of them. And they do tend to linger around the same level of equipment, that value equipment. And when over 60% of homeowners can't afford a $400 expense, a sudden $400 expense is more than what 60% of homeowners in the U.S. cannot afford. They're buying the value line. And so this is happening an awful lot. And so what we do, because it works, is we put in a system that's too big, because we look at the unit and we say, all right, well, this is a 3-ton, so we're going to put in a 3-ton. The 3-ton was working before, and that 3-ton was working better, because it was better at removing moisture. But we put it in, and we put it on this crap duct system. And what happens, as we learned from Ed yesterday, when you give a system less air to its ability to remove moisture? It improves it. Just to be pedantic, if you're not sure what pedantic means, it means pain in the ass. Just to be a pain in the ass, Ed, the latent doesn't always go up, the capacity doesn't always go up, the percentage does, right? Sometimes the number goes up, but you will reach a point of diminishing returns where you don't have a larger latent capacity, but you do have a higher percentage. And since it's all about runtime, I'm splitting hairs, I'm being a pain in the ass, right? Because if I can get more moisture removal per run cycle, I might still be comfortable. My homeowner doesn't know that this is cycling on and off more than it should. The homeowner doesn't know that it's operating at pressures it shouldn't be. The homeowner doesn't know any of that. They know they're not uncomfortable. They know that the level of comfort in their house hasn't changed that much. When in reality, you've done a bad job, right? Because this could have been more efficient. Now, this is where you get into some weird territory that may be deeper than what we have time for. Because am I going to replace their entire duct system on every retrofit job? Probably not, right? Although I've worked with companies where that's what they do, right? Like, yeah, your system is more than 12 years old, replace it, or we're not doing work with you. Like, that's a thing they do, and they make money on it. But you maybe could add return, or you could maybe pay attention to what filter you use, or you maybe could suggest ECM constant torque blower that can handle the airflow, or you maybe, and this is why understanding how it works is super important. Because in order for you to determine what your maybes are, what you could do, you need to understand these factors, right? So, also, by the way, what happened when this system was originally oversized and underducted? Some service guy came out, hooked up some gauges to it, and fixed the refrigerant. Now it works, right? I'll spend money on my 3-ton compressor while it does 2 tons of cooling. Yay, right? So we know all this stuff. We reviewed all this stuff, right? A 2-ton used to be a little house. Now it's a big house. Coils used to let air through them. Now they stop it. Well, they don't block air completely, but the fact that microchannels are more aerodynamic. Why do they use them? Because if they didn't, they'd be way less aerodynamic. Coil pressure loss has gone up. Filters used to keep the cat out of the furnace. Fun joke that everybody seems to like. Now we're stopping microns of particles. The fan's being moved around. Everything's changing underneath our feet. And we still expect to be able to do it the same way and have it work. Right? And, it used to work, guys. It did. I'm not saying you all did bad work and shame on you and you did terrible jobs and listening to the people who taught you was wrong. No, this stuff used to work. Yeah. But why did it used to work? Because if you don't pay attention to that as the industry shifts like a San Andreas earthquake underneath our feet, we're going to fall over. Right? We have to pay attention to why it worked so that when they change stuff on us and don't necessarily tell us about it. Yeah. I was crazy impressed with Rob's presentation before mine, where he stood up here with the Mitsubishi product and told you some of the things that they're bad at and what they've found to be good solutions to that. There's not a lot of manufacturers that I've found that are particularly good at that, and I was really impressed. You're not generally going to find that in the entire industry. And that makes, so in regular HVAC classes, you're responsible for your own safety, right? So you're responsible for knowing what the changes are to your product and how they will affect you, right? Nobody else can be responsible for that. So you will recognize this slide. We've already looked at it, and same with this one, and same with this one. And this is, you knew this already, right? Because you knew when it's the other guy's job, you knew that long run wasn't getting enough airflow, right? And when it's the other guy's job, you knew the filter was killing you're the homeowner, right? When the homeowner put it in, you knew it was the filter's fault that they weren't getting enough airflow, right? And it was when the other guy went around the world to get to that supply run. We knew that was bad work, and it would. But guys, you are slowly being pressured to do all of these things by the builders and the homeowners, and we're squeezing these things in here. Like, you could take the high road and be like, I won't do a system unless we do it this way, but you're going to eventually run out of work, right? If you can't dictate the conditions in which you work, you're going to have to adapt how you work, right? If you can't say, I will only work on jobs like this, then you need to be adaptable how you do those jobs, right? Or else it's not going to work. Everything has to stay in balance. That's what we're doing here, man. Right? Bigger fan, smaller duct. Smaller fan, bigger duct. Longer runs, bigger duct. Big ass filter eating up all the energy. Make your ducts bigger. There's limits to it, but that's what good design is. And by the way, that's what our software will help you do. All right? You start with your load, Manual J. Figure out what the building's needs are. Load calculations, by the way, here's a good thing an annoying sentence is good to remember. Load counts don't tell you what equipment you need. Load counts tell you how much heat the building gains, how much heat the building loses, how much moisture the building gains. Then you use your Manual S. The equipment tells you what it can do. So you look up equipment, find one that will do what you want it to. Right? I know what my needs are. Find one that can give me what I want. Right? Were you in Colorado or were you in Arizona? California. All right. So you're not high altitude. Because when you're doing Manual S, that's where it gets really fun and weird, right? I go up to Colorado, I take that number, and it's all dry, and so it's a super low number, and then you get to shave off another 20% of its capacity because of the thin air. And, yeah. So you have to do all of that because this is what it's capable of, right? Look it up, right? And then once you have that equipment, now you have to look at what that equipment can do. How much friction resistance can it handle? Okay, so let's make a system that creates that much restriction, but no more, right? And I have a few things that I can toggle and slide if I'm willing to be flexible about what filter I use or what coil I match it up to. Am I willing to build that increaser or not? Do I sell? I mean, I know guys who do nothing but sell variable speed just to get out of this to a certain degree. You do that. But there's consequences to every action, right? This is why you got to do this. So I promised that you guys could beat me up if you wanted to, and I told you, verbal equivalent of a steamroller, right? If you've got anything, or like you want to pick a fresh fight, you could do that too. Yes.
This is software question.
Software question. Let's see some software.
Yeah.
Fire away.
So, in your
somewhere?
software, you enter your friction rates.
No, you don't. You enter your static pressure.
You
can enter a friction rate. You shouldn't.
Yeah, you enter your
Static pressure,
right.
external static pressure.
But you have heating and cooling.
Oh, it's
You know
going
what
to
I'm
be that
saying?
question. Man,
Yeah.
that's a tough one. So, Allison skimmed this one. You can do heating and cooling separately, or you can do them together, right? So how many duct systems do you have in a house? Yeah. So you can design heating and cooling separately, and you're still only getting one duct system.
That's one.
Right? So, the theory is, and this is, so it's another situation where it's good to know how and why, right? The theory is, one season's going to have a much higher amount of airflow than the other. That's not always the case, right? But restriction, first of all, the theory is that you should do heating and cooling separately, and you're going to love this. You should seasonally rebalance every system twice a year.
Yeah, absolutely.
There you go. Okay? Yep. So we'll uncheck the little box for heating equals cooling, and you'll have one duct system, and it'll be sized to the worst case, and it'll go. See, the risk you run is we're going to take a hypothetical, if you have 1600 CFM for cooling and 1200 CFM for heating, or whatever it is, you have a room now that needs more heat than it does cooling. But because your total cooling CFM is lower, we're not going to give it a bigger duct. Because proportionally, the actual CFM number you designed for is lower than the cooling CFM would have been. So we're not going to make it a bigger duct. I like heating equals cooling design. Personal preference. That wasn't a MyTech recommendation. That's me. Because I'm of the opinion that you should put balancing dampers and everything, and if you're not going to seasonally rebalance, at least you can adjust to comfort. Right? I know a lot of guys say you get one free balance from us. Right? We're going to install it. If you don't like what you get, we'll make one adjustment. Right? And that gives you the ability. When you go with the larger of the two, you're always going to have the ability to do a proportional adjustment. Right? Because if you don't give it a bigger duct, it's really hard to get more air into it. Even if it's sized for the amount of heating CFM it's supposed to get,
So going back,
duct design is proportional. So if you don't use your heating equals cooling,
so maybe we should have our suppliers or inventors invent zone and dampers with heating and cooling separate set points.
good luck selling it.
Yeah.
Right? Because actually, this is a much bigger concern in up north than it would be down south, right? If I go far enough south, I answer, like if I was teaching this, you guys were a class and you were all from Miami, I would say turn the button off and do cooling, right? If I'm in Austin, turn the button off and do cooling. Like nobody cares about heating, right? We have one cold night and we're asleep, right? But when you're in a climate where both of these things are going to be happening all the damn time, you get homeowner preferences. You get me. I would always rather be cooler. I'm a nutcase. Like this is I literally consider this weather to be hot, right? My thermostat, when I'm at home in the winter, by the way, so we were talking to the last meeting, we were talking about like, we should just take the number off the thermostat. I love that idea. When you're talking with a homeowner, if you want to know what their comfort level is, a lot of times it's really a good idea to ask them, what temperature do you set the thermostat in the winter? The winter is going to be dry.
Oh,
right.
Right.
So what do I set my thermostat in the winter? 62 degrees. So, but you don't know that about me, right? So would you want to design my system for heating or cooling? I live in Boston, right? Or I live in Massachusetts. Oh, it should be heating. That's a heating climate. Yeah, this is a cooling human, right? So I'd like to be designed for both. Involved.
Come back.
Yep, I'll swing back. Anybody else? There's Nate. How's it going? Oh, I love easy ones.
You steamrolled me with so much information I can't get it.
Sorry, man.
It's all good. No, I'm loving it. I have laughed this hard a lot. Seriously. So, say you have a 25% turn down, or something like you can turn it down 75%. So use 25%.
Yeah.
Piece of equipment. How many of these challenges does that essentially solve?
Yeah.
How many of these challenges?
The flow challenges and a lot of the duct design challenges you're talking about. Like our experience is we do